I was given this topic, and I assume that hopefully that this reflects the concepts, engineering concepts to discuss. And I think it's an interesting topic in itself as the VAD space has become a little more complicated. And there's a number of important features that now differentiate the pumps. And so today we're going to review some design features, including flow characteristics, impeller suspension, control of pump flow, and waveforms. There's really two basic designs for continuous flow rotary pumps, those of a centrifugal and axial. And really what differentiates the two pumps is the angle at which the flow exits the pump. So in a centrifugal pump, pump outflow is 90 degrees perpendicular to the axis of rotation of the impeller. And for an axial flow, that the outflow is 0 degrees or parallel to the axis of rotation or center line of the pump. Now, the impeller or center device in continuous flow rotary pump is suspended in a variety of mechanisms. In the simplest design, it's a mechanical pivot design where there's actual mechanical suspension of the impeller, where the impeller is connected to a stator or a mechanism that uses a ball and cup kind of design. Now, this design is simplistic, but has a number of limitations. It represents a point of friction. And in order to dissipate heat, blood flow needs to, you need a continuous source of blood flow to prevent heating of the bearing. And the bearing actually rides on a thin film of fluid, so there's not actual direct contact between the bearing and the cup. These are made of unique materials such as quartz, and they're very resistant to wear. And so these types of pumps, although they are mechanical in design, can last for years and years and years. But they do have the limitation of friction. Now, another important type of bearing design is a non-contact bearing or limitless bearing. And essentially here, the bearing is floating in blood. So there's no contact, there's no mechanical suspension to the bearing. And these are complex systems now because the bearing has to be, or the impeller has to be controlled in 6 degrees of freedom. So there's rotational movements around the X, Y, and Z axis, as well as translational movements, those movements which are not associated with rotation. And then importantly, in these types of designs, at least one axis has to be controlled by a active motor, which will be able to spin the impeller within a magnetic or hydrodynamic field. So there's three types of, or there's several types of non-contact bearings or levitation systems. One, the levitation system can be magnetic, and you can either have active magnetic levitation, so there's an electrical current going through the magnet, and that magnetic force can change with the change in current that's being passed through the magnet. Or you can have a passive rare earth magnet where there's a constant magnetic field. Or you can have a levitation system that is called hydrodynamic, which depends on fluid field forces. Or you can have a combination of both magnetic and hydrodynamic forces. Now here's an example of a totally magnetically levitated system, and this system is currently available in the HeartMate 3 device. And so what is unique about this system is that with magnetic levitation, you can have large gaps between the impeller and pump housing. So in this case, gaps between the impeller and housing are 1 millimeter on top and bottom, and 500 microns along the edges. Now, what the issue with magnetic types of levitation systems is the scalability. You cannot make these systems very small because as you make them smaller, the magnets begin to lose strength and they begin to lose efficiency. So reducing the size of these types of centrifugal pumps has limitations. And so the magnetic strength affects scalability, motor efficiency, and also affects gap distance. Now, a hydrodynamic impeller suspension, here's an example of a hybrid system that requires both magnetic levitation and hydrodynamic levitation. And this is an example of the levitation system in the Medtronic LVAD device. And here, fluid-filled forces actually push down on the impeller as it rotates, and those forces are opposed by a center magnet that lifts the impeller up, and those counterbalancing forces provide suspension of the impeller without contact. Now, one of the limitations of a hydrodynamic bearing is it depends on fluid forces, and so those forces dissipate quickly as opposed to magnetic forces. So the distances between the surfaces of the impeller and the pump housing are much closer in a hydrodynamic type of suspension compared to a magnetic type of suspension. Those distances are on the order of about 50 microns compared to 500 or 1,000 microns with a magnetic levitation system. So the advantages of a totally magnetic levitating suspension system are that its rotation is independent of rotor speed. So a hydrodynamic system, in order to generate force, has to be spinning. So in the absence of spinning, the impeller in a hydrodynamic setting could actually touch down and touch the pump housing. So again, the magnetic suspension system is independent of rotor speed, and that allows variability in operating a full range of pump speeds and can accommodate a differing afterload and preload conditions, and also allows for large gaps. Now, pump flow characteristics are unique for every pump, and there's a unique relationship between the pressure head and pump flow. So pump flow is inversely proportional to the pressure head. So as the pressure differences increase between the left ventricle and the aorta, pump flow decreases. And as the pressure differences get smaller, the difference between the left ventricular pressure and the aortic pressure reduce in size, then the pump flow is greater. So you have a situation here where you have varying degrees of pump flow depending on the pressure head. And importantly, then also flow is dependent on motor speed. The pump head characteristics differ for each pump, and traditionally we've been taught in a simplistic fashion, we've always been taught that centrifugal pumps have a flat relationship between pressure and pump flow, and axials have a more steep relationship. But a better way to think about this is that each pump has its own unique pressure flow relationship. So independent of whether it's a centrifugal pump or an axial pump, every pump has its own pressure flow relationship. And here's an example of different centrifugal and axial pumps, and you can see that their pressure flow characteristics differ amongst the pumps. And each line represents a different pump speed, so every pump has a unique set of characteristics for that. And so the general, what is the differences between a steep and a flat pressure flow relationship? Generally speaking, in a situation where you have a flat as opposed to a steep pressure relationship, any change in pressure represents a larger degree of flow for a flatter relationship. And so in that situation, you're likely to see more flow variability during the cardiac cycle. As the cardiac cycle changes, there's differing pressures through diastole and systole, you would see more flow variation with a pump that has a flatter pressure flow relationship than one that has a steeper pressure flow relationship. Now, to make the situation even a little bit more confusing, here's a comparison of the HeartMate 3 and the HeartMate 2 pump. Now the HeartMate 2 pump is an axial pump, and the HeartMate 3 is a centrifugal pump. But the pressure head for flow characteristics of each of these pumps are very different. And at the higher flow ranges, lower pressure, actually the centrifugal pump has a more steep relationship than the axial pump. And at the lower flows or higher pressure areas, the relationship is much more flat for the HeartMate 3 as compared to the axial pump. So again, this just reinforces the idea that the pump flow characteristics for each pump are similar, are unique to each pump design. Now, there is a number of ways of adjusting pump flow and a number of ways of operating the pump. There could be fixed speed operation, or you can base flow on physiological control algorithms or non-physiological control algorithms. And we know that in a fixed speed mode, the pump has hydrodynamic properties that allow a limited Frank-Starling mechanism. So when differences in pump pressure change during the cardiac cycle, so during During diastole, when there's large differences in pressure, flow is less, and during systole, when pressure differences are less, flow is more. Now, you could add preload. If you increase your preload, you will see more flow with the pump, and if you reduce or increase your afterload, you will see more or less flow with the pump. So the pump has some inherent hydrodynamic properties that allow it to respond to changes in afterload conditions or preload conditions. However, these changes are very limited. And so in a pump performing in a fixed speed mode, it's generally less sensitive to preload changes and more sensitive to afterload changes compared to the native heart. And so that results in underpumping or overpumping in certain situations that can give rise to congestion or heart failure or give rise to suction events. So there are other ways to control pumps other than a fixed speed mode. And those, in order to do that, you need inputs into the pump. So you can have pump power as a measure of controlling pump flow, and you can have a pump pressure. So the pump can pump based on the feedback from pressures. And that would be the ultimate design. Unfortunately, in clinical use today, there's no pump that uses pressure as a feedback mechanism to control flow. And ultimately, what we'd like would be left ventricular pressure to guide flow adjustments. Now, in a situation of overpumping, where you can actually have a suction event, there are pump designs that use control mechanisms to try to prevent some of the adverse events. So one way of doing that is something called a pulsatility index. And pulsatility index looks at peak power minus minimal power over average power. And it's an indexless number. And based on that can be measured in milliseconds over a course and averaged over a course of time. And then when there's dramatic changes in the pulsatility index, if there's a rapid decrease in pulsatility index, the pump or the computer interprets that as a suction event and then can control speed or reduce speed. So these are inherent control mechanisms that look at flow adjustments to prevent some of the untoward events of the LVADs. Now here's an example. Now there's two pumps in practice, the HeartMate 3 and actually the Jarvik pump, where there's inherent changes in speed that occurred during the pump, not based on physiological measures. And in the Jarvik, every 8 seconds, there's a slowdown in speed, which allows opening of the aortic valve and washing of the aortic root. And here, there is in the HeartMate 3, there's a speed up and speed down. Now, this algorithm is not to induce a pulse, but actually just to wash the pump. So it's really designed not on a physiological measure. Now, another unique thing about, another unique issue with devices are waveforms. And waveforms provide important information on pump control. And here's an example of waveforms from the Medtronic HVAD device. And these are very informative and help with clinical management. And on the left panel, you can see a situation of low pulsatility, and inotropes are reintroduced back into the patient. You can see improvement in contractility and flow variation during the cardiac cycle. And in the second panel on the right, you can see the impact of hypertension on pump flow. So hypertension reduces pump flow, causes more native output with more pulse and more variability in flow. And when you reduce the afterload, you can see that the actual flow goes up and the degree of pulsatility goes down. You can also use waveforms to help in other ways, such as on the left panel represents power readings. And just by power measurements, this is an example of pump thrombosis conditions, differing pump thrombosis. And this can actually inform physicians on the best way to treat pump thrombosis in these cases. Waveforms can also tell us a little bit about resting filling pressure. So on the right panel, the rise in the flow during the diastolic cycle can tell you, can give you information about diastolic filling pressures. And so that information can also be used to physiologically adjust pump flow. And here's an example of a waveform from the HeartMate 3 pump. And again, if you look at the far right of the panel, you can see there was an abrupt drop in flow consistent with cardiac tamponade. And so those are signals that can be very informative in patient management. So in summary, there's important features that distinguish continuous flow rotary pumps, and that includes flow characteristics, biocompatibility, and also there are ways of informing patient management and important differences in user interface. Thank you.